So all the matter that we are made out of, the Earth is made out of, other planets and stars, all the kind of typical matter that things are made out of is made out of different types of atoms. Now there are other types of matter, but not that can be used to like build houses or build planets or anything like that. Like you have kind of neutrinos, which we can't even really catch or stop them. There's antimatter, which would explode upon contact. So there are different types of matter that I'm not including in this discussion. Right? So all of the different types of atoms that we can use to build molecules or air or houses or anything are going to be listed in the periodic table of the elements. And elements or atoms, I use those two words interchangeably. So hydrogen, and then we come over here. I'm in the front cover of your book, by the way. Helium, carbon, oxygen, neon, aluminum, iron, nickel. They all have their own different structures. So let's go through that. So let's take carbon, for example. So carbon has to have 6 protons in its nucleus. And most carbon also has 6 neutrons in the nucleus, but it might have 1 more, might have 1 less, might have 2 more. So let's just say likely has 6 neutrons. Right. But it has to have 6 protons, because if it had 7 protons, it would be called nitrogen. The 6 protons is what defines it as carbon. And the number of protons in its nucleus is also called its atomic number. And instead of atoms, I could have also written elements. That's just a redundant way of saying it. Now I think I'm wandering into section 10.2. So the symbol for carbon is just going to be a capital C. And the atomic number gets written down here. And these are redundant, right? Because if it has 6 protons, it is carbon. If it had 8, this would be oxygen. And instead of writing a C, we would have to write an O. So this little number down here is the atomic number. Which is the number of protons. And the abbreviation for that often is just Z. Sorry. Now, the typical form of carbon usually has 6 neutrons, and that could be written down over here. So how about we label that number of neutrons. Or you could call it the neutron number. Right? Its abbreviation is N. Right? And like I said, for a certain carbon atom, it'll probably have 6 neutrons, but it is possible for it to have an extra one. It could be 7. It could be 8. And then up here, we would usually write the mass of this atom, kind of counting up the number of protons and neutrons because they weigh much more than the electron. So in here, the protons would give us 6 units of mass, and then another 6 units of mass from the neutrons. So it would have a total of 12 units of mass. So we could write that up there, and that would be our atomic mass number. Now, if I could have picked a letter to abbreviate that, I would have picked M, but the abbreviation is capital A. So if you wanted to find A, the atomic mass number, you could just add up the number of protons and the number of neutrons, because we are ignoring the mass of the teeny tiny electrons. What if you needed to find N, but you knew A and Z? You could find N by doing the total number of protons and neutrons A, and then subtract off the number of protons. So that almost looks like I have one more corner to cram some more information in here, and we do. you should tell some information about the electrons. How many electrons does this thing have? So how we're going to do that, though, is we're going to basically say, is this carbon neutral as a whole? Or is it positively charged as a whole? Or is it negatively charged kind of as a whole? So how about we say that this carbon happened to be charged with a +1? What would that mean? So if this carbon atom had an overall charge of +1, it means that it had one more proton than it had electrons. So then we know that the number of protons is 6 because it is carbon. So Z, the number of protons, was 6, and we need one more of these than the electrons. So then we could say that the number of electrons was equal to 5. So basically this atom is missing an electron. It got ripped off. It got taken somewhere else by some other atom, leaving it with one too many protons with a charge of +1 unit. Right? If an atom has an overall charge, +1, +2, -1, -2, it's called an ion. It's just another name it's given to it when you could just really say it's +1 or +2. It's also called an ion then. What if this was kind of a weirdo carbon and it had an extra neutron, one more than usual? What would it look like? We would say that it was a carbon still, because it would still have 6 protons. And now it's got an extra neutron, so it would have 7 neutrons. How many kind of units of mass does it have in its nucleus now? It's got 6 from the protons and 7 from the neutrons, so it'll have a total of 13. And then should we still imagine that this one is missing an electron, like up here? Let's just keep that the same way. Let's just say +1. So we'll say that it has 1 extra neutron. And maybe you don't know what typical is. How do you figure out what typical is? I would usually just go to my periodic table and find carbon. And so what this is this is kind of an average value. And see how the average here is much closer to 12 than it is to 13? So 12 is typical. But you know, sometimes it might be a little bit larger, so that's why this average is a little bit larger. Sometimes you might get a 13 or 14. But usually a carbon would have a mass of 12. And like oxygen here is practically 16. So I would say almost all the times oxygen will have a mass of 16. That would be 8 protons, and then 8 neutrons. That would give you the 16 for the mass. But sometimes you can tell it's not perfectly 16. Part of that has to do with nuclear energy. Let's not get into that right now. But part of that is also just, you know, like sometimes a few oxygen atoms would be missing neutrons, and so this average would be less. Right? So this would still be an ion, missing an electron. But now that it has 1 extra neutron, we can also call it an isotope. So you could say that this atom is now also an isotope of carbon because it has a weird number of neutrons, a non-typical number of neutrons. And depending on the case, a lot of these don't get written out. Like if it was not an ion and it had like an overall charge of 0 and it was neutral, we wouldn't even bother writing that most of the time. And since these two are perfectly redundant, if it has 6 protons, it has to be carbon. A lot of times this is not even written. It's implied to be there. And then if you knew that carbon had 6 protons and it had a total mass of 13, you could pretty easily figure out that the number of neutrons is 7. So oftentimes that isn't even written. So if the numbers are missing, just assume that they're the normal typical values, or, neutral. The number of protons and the number of electrons are what's really important for its chemical properties. Like what molecules can it form? Right? Is it reactive? Is it stable kind of on a molecular level? Now, some atoms are so kind of bulky and unwieldy that they're unstable and they could just kind of disintegrate and fall apart and become radioactive. And that happens when these are kind of very different from each other, or when they get very big. Like uranium is a huge atom. It has 238 for its mass, so it has a lot of protons and neutrons. At that point, it's just so big, it becomes unstable, and that's why uranium can disintegrate and become radioactive. Now, I was calling these units. Let me just show you how to convert them into SI if you ever needed to do that. So let's take this 13, and we'd call those atomic mass units. And abbreviated, it would just be 13U. And then the conversion to kilograms is 1U is equal to 1.667 times 10 to the negative 27th kilograms. So that's our conversion factor. And what about the charge on this? Maybe it had a charge of +1 unit, but that's kind of an electrical amount. And so we would say it has the charge of +1, lowercase e, which is the amount of charge on a single electron or a single proton. And the conversion there, 1 electron charge or 1 proton charge, would be equal to 1.60 times 10 to the negative 19th coulombs. So how about we find the mass of the 13 carbon in kilograms for carbon 13. Right, its mass was 13 atomic mass units times the conversion factor. 1 atomic mass unit is equivalent to 1.667 times 10 to the negative 27th kilograms. Atomic mass units would cancel out. So 13 times 1.667 times 10 to the negative 27th. 2.1671 times 10 to the negative 26 kilograms, which is a very, very tiny amount of mass. And we're going to treat that 13 kind of as a perfect 13, so we're going to ignore its sig figs. That was good to 4 sig figs, so I should probably just round this to 4 sig figs. Now, if we wanted to find the electrical charge of that, so it would be a carbon atom with a +1 charge. And let's find that in SI units, which is coulombs. And there's the C for coulombs right there. So we had a charge of +1 in kind of atomic units, atomic charge units, the charge of electrons, times the conversion factor, where 1E is equal to 1.60 times 10 to the negative 19 coulombs. Those cancel out, so we get a +1 times the conversion factor, so we'll really just get the same value again. I wrote the plus out because I wanted to. You don't have to. Your book then does a little bit on the strong nuclear force. So if we imagine the inside of the nucleus, which only has protons and neutrons. Like, how does it stay together? Because all the positives should repel. They don't like being together. They're pushing apart from each other because they're positives. How do they stay together? There is another force that's even stronger, and we call it the strong nuclear force. And you can only notice that force on teeny, 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 tiny scales. Like not even for the whole atomic nucleus, just a little portion of it. So only these particles in this little region feel attracted to each other because of the strong nuclear force. They don't even feel the attraction to these from the strong nuclear force. But then you could say like this one would be attracted to its nearest neighbors, and this one would be attracted to its nearest neighbors, and that one would be attracted to its nearest neighbors. So as a whole, this thing can be stable and be held together by this strong nuclear force. But when it gets too big, when there's around 83 positives, 83 protons, it starts to kind of lose cohesion. It starts to be able to just kind of naturally, spontaneously, break apart. Think uranium breaking apart. When it is unstable and it might break apart, you could call it a radioactive one. Now remember that light, visible light, is a type of radiation in that it is energy traveling outwards along radial lines from its source. And in that way you could almost even say that sound is a type of radiation. It's energy traveling away from the source, kind of outward. Now, when people say radioactive, usually they're meaning the dangerous stuff that can happen when atoms fall apart or change. Radioactive atoms. Let's say atoms. Atoms can decay or be radioactive. In 3 different ways. Alpha decay, beta decay, and gamma decay. And these are just Greek letters really. Alpha, beta, and gamma. Now what happens during alpha decay is a big unstable nucleus will just kind of emit a helium nucleus. Your book gives us an example, but let me talk through it. So, the book gives us an example of starting off with the element of thorium. Now, thorium has 90 protons, and this atom of thorium that we're talking about has 232 kind of mass units, protons and neutrons added together. So it's got 142 neutrons. Now, this just happens to be unstable. It can do an alpha decay, which means a helium nucleus is going to break off. And so helium is abbreviated with He. And by definition, it has 2 protons. And a helium nucleus has 2 neutrons. So it has a mass of 4. So then we can kind of play the game of what was left. So it had 90 protons and it lost 2. So it's going to have 88 remaining protons. It had 142 neutrons and it lost 2, so it's going to have 140 neutrons. Now I'm going to look up in the periodic table, what is 88? Atomic number 88. Radium, abbreviation Ra, and it had 232 kind of mass units, and it lost 4. So it's going to be 228. Right? So this is kind of your beginning, and this is your results. And if you say it's going to do an alpha decay, you're saying one of these is going to break off. A helium is going to break off. And overall, this isn't really dangerous at all because helium is a gas. It could, go into the room and you're breathing it, but it's not dangerous. You can breathe helium for fun as long as you get oxygen in there too. This so happens to be unstable and poisonous, but so was this. This was also unstable and poisonous. These helium atoms could be coming off at high speed. And that might be dangerous if these helium atoms come at us with high speed, because if they hit us hard enough, they could, damage our DNA or something. But helium atoms are stopped with a sheet of paper. So as long as you take your thorium here and kind of put a sheet of paper between it and yourself, you will be safe from the alpha radiation from those helium atoms. Beta decay basically means that it's going to give off an electron instead of a helium nucleus. It's going to give off an electron. And it's going to do that because one of the neutrons is just going to fail. So one of the neutrons kind of goes radioactive by itself and turns into a proton and an electron. Now the proton will probably still be stuck in the nucleus, but the electron will likely escape, and so that would be the radiation that leaves. The electron is emitted. So your book gives us an example of carbon-14, which is a not stable version of carbon, the radioactive form of carbon. And because it's carbon, it has to have 6 protons. So for this version of carbon with 6 protons and a total mass of 14 in the nucleus, that means it has 8 neutrons. And when it undergoes beta decay, because it's not very stable this way with a mass of 14, it'll get an extra proton by losing a neutron. So this will go to 7 protons and 7 neutrons. And now that we have 7 protons, we can't call it carbon anymore. We just have to call it nitrogen, which you can look up in a periodic table. And the total mass here in the nucleus is still 14. I'm like, it is losing the mass of an electron, but it's so tiny we're ignoring it. And then we could also say, not only did it end up with this, but it also ended with an electron escaping. All right, a gamma decay basically just means that it's going to give off some high energy light. High energy light can be called gamma rays, right? So gives off high energy light. So your book gave an example of lead with a mass of 204. And the notation your book uses has a little asterisk right here, basically meaning it was high energy. You can imagine it like kind of vibrating extra fast. Its electrons would be in a high energy state. And then when the electron moves to a lower energy state, which we haven't really talked about yet, so just go with it for now, it would become a lower energy form, so we don't have to put that little star here. It's going to lose some energy and just kind of give off high energy light. And the other numbers on here that I didn't write, they would just be constant. They wouldn't change at all. So I kind of think about this as just a conservation of energy. Like before, the energy was kind of stored in its high energy electrons. And then now that energy is leaving the atom in the form of light. All right, so kind of going back to safety and whatnot, alpha particles can be stopped by like a sheet of paper. It's not too hard to stop alpha particles, to shield yourself. Beta particles, basically electrons getting flung out, you could stop them with some aluminum plate. Right, so usually they're not too hard to shield yourself from them either. Okay. Gamma rays are the harder one. Basically this high energy light that is coming from these particles. So while you might have a bunch of uranium in a nuclear reactor, it will be giving off helium atoms and it'll be giving off electrons, but it's also giving off high energy light. And that high energy light has the possibility to give you cancer and damage your DNA. And in order to shield yourself from that, you need a lot of lead and or concrete between you and the radioactive material. When I was at the U of M as a student, I worked in the nuclear lab for a while and had some training and had to deal with the Nuclear Regulatory Committee and had some fun stories from that. But our radioactive material was californium, not uranium. And it was inside of this huge kind of lead room, or concrete and lead room. And you could there was a little drawer, a concrete lined drawer, so you could slide samples in and out to kind of expose them to the radiation and then bring them out and study them. But one thing that they made sure to tell me was that the most dangerous thing in that room was the dust. Because like your body, your skin can protect you from alpha and beta particles pretty easily. The concrete and the lead was protecting us from the gamma radiation. But some dust could go in and out of that drawer as you're opening and closing the drawer. And that drawer could be radioactive. And if it gets into your lungs or into your stomach, then you no longer have your external skin to protect you. It is in your body. So we had, I carried a Geiger counter and I wore a little dosimeter as well to measure my exposure. But really what we had to do was keep the room clean and had like a super expensive HEPA vacuum to make sure that that dust was kept under control.